Telusio is a leading digital solution provider for carbon emissions on product level, such as batteries. With their innovative AI-based solution, the Munich-based company enables a broad range of manufacturing companies to determine the carbon footprint of their products.
Hi, my name is Dr. Weibl, founder of Telusio. With our AI-enabled software, we as Telusio support producing companies, for instance in the battery sector, with modeling their carbon emissions.
Hi, my name is Nina Thalberg and I'm a senior project manager at Telusio. I'm involved every day in the calculation of carbon footprints.
Let me start by saying this. Batteries are the backbone of decarbonization. They are the driving force behind electrical vehicles and renewable energy storage, both of which are essential to meeting global climate goals. Calculating these carbon emissions of batteries ensures that their production processes are as low carbon as possible. This not only amplifies their environmental benefits, but also brings us closer to a sustainable future. Now, let's talk about manufacturing. Producing batteries, especially lithium-ion batteries, is incredibly carbon intensive. It consumes significant amount of energy, often sourced from carbon-heavy processes like mining and refining raw materials. By calculating these emissions, we gain transparency, and with transparency comes action and the ability to target and reduce the carbon emissions of batteries. On top of that, batteries depend on a global supply chain. Carbon emissions vary dramatically based on the energy sources and practices used in different regions. When we calculate emissions across the supply chain, we can identify carbon hotspots and develop strategies to address them. Here's a concrete example. Producing an e-bike battery pack can result in 50 to 100 kilograms of CO2 equivalent emissions. This highlights why it's so critical to calculate and understand these emissions in order to mitigate their impact. The relevance of calculating battery emissions is growing. Market and regulatory changes are reshaping the landscape. On the political landscape, the battery pass regulation most recently has increased the pressure on the battery sector. Within the next years, many battery types sold in the EU will require carbon footprint disclosures. Further, by 2027, life cycle emissions thresholds will be in place, potentially prohibiting carbon-intense batteries from entering the European market. These regulations will become even more demanding for battery manufacturers in the future, enforcing transparency and subsequently emission reductions. These rules aim to enhance transparency, encourage sustainable sourcing, and drive innovation in low-carbon battery technologies. On the consumer side, shifts are happening. Consumers and business demand more sustainable products. Overall, transparent carbon footprint will provide manufacturers in the battery sector with a competitive advantage. When it comes to calculating emissions, there are two primary approaches. The first is the activity-based method. This involves using detailed data on materials, energy usage, and processes. For instance, we might measure electricity consumption in kilowatt hours or raw material usage in kilograms. This method is the gold standard. It's accurate and pinpoints emission hotspots, showing us where improvements are needed. The second approach is the spend-based method. This estimates emissions based on financial expenditures. While it's useful when detailed data isn't available, it's far less precise. It doesn't allow for a deep dive into the supply chain and therefore doesn't offer the opportunity to gain strategic insights. Furthermore, emission calculations depend on the system boundaries. There are three main perspectives. First, cradle-to-gate covers raw materials extraction, processing, and battery production. Second, cradle-to-grave includes the use phase and end-of-life processes like recycling and disposal. Third, cradle-to-cradle focus on a circular economy, emphasizing recycling and reuse. Several trends are reshaping the industry. First, there's growing standardization in calculation methodologies. This ensures comparability across products and manufacturers, a vital step as regulations tighten. Second, digital tools are becoming increasingly important. They are helping companies gain transparency into fast-evolving supply chains while dynamically identifying areas for improvement. Third, there's rising demand for third-party verification of carbon footprint calculations. This boosts credibility and ensures compliance with new regulations. The industry is also innovating to minimize the carbon footprint of battery production. For instance, manufacturers are switching to renewable energy sources such as solar-powered gigafactories. Sustainable material sourcing is gaining traction with methods like low-carbon lithium extraction and recycled cobalt. Some companies are developing alternative battery chemistries with a lower environmental impact. Advanced recycling technologies are closing the loop, reducing reliance on virgin materials and supporting circular economy.
To calculate the carbon footprints of batteries, we rely on two types of data, primary and secondary data. Primary data is our top priority. It comes directly from suppliers and manufacturers and includes details like energy use, material quantities, and production processes. But when primary data isn't available, we turn to secondary data from trusted sources, such as scientific life cycle inventory databases, industry benchmarks, and peer-reviewed studies. For example, when we need to model emissions from mining raw materials in global supply chains, secondary data is often our best option. But what can we do to ensure the validity of the data? For that, we have different methods based on the channel where we have collected the data from. If we've been given primary data by suppliers and manufacturers, we always check if the results are in line with other verified results or scientific studies. For secondary data, we rely on scientifically proven modeling methods, cross-referencing our results with industry averages and benchmarks. Lastly, we regularly update our data to reflect advances in technology and changes in energy sources. Using an activity-based approach instead of a spend-based approach provides a comprehensive understanding of emissions throughout the supply chain. It helps us pinpoint emission hotspots and take targeted actions. If we're looking into the two major steps along the value chain of a battery, raw material extraction and production, this will become clearer. So let's start with the raw material supply and compare some raw materials. First of all, lithium. For lithium, we see one of the great causes of high emissions when extracting it from hard rock mining, as it is a very energy-intense process and therefore is causing higher carbon emissions than other materials might. Obviously, there are many other negative consequences to the environment when hard rock mining, so a less carbon-intense approach is extracting lithium through brine extraction. Another example would be nickel. For nickel, we see a lot of emissions being caused when smelting and refining the material. And that brings us to the next process step, the production. Processes like electrode manufacturing, cell assembly, and formation cycles are highly energy intense. And the electricity grid used in production plays a huge role. A coal-based grid versus a renewable one can make or break the carbon footprint of a battery. By analyzing the different aspects, we can identify steps in a production chain that cause a lot of emissions. In the next steps, those can be tackled, whether that's sourcing materials more sustainably or improving production efficiency. Therefore, emissions can be reduced, leading to an overall lower carbon footprint of the battery. It's about being strategic and making real progress. There definitely are some challenges. The first big one is data gaps. Getting primary data from upstream suppliers can be incredibly difficult, especially given the global structure of the supply chain. And even when we do get data, the quality and consistency often varies across different regions and suppliers. The second challenge is the complexity of supply chains. Batteries involve multiple tiers of suppliers, and tracing emissions all the way back to the source is a great undertaking. On top of that, raw material sourcing strategies can change dynamically, which means that carbon footprint isn't static, it evolves. But here's how these challenges can be tackled. First of all, increase your chances on high-quality primary data. It is crucial to work on great partnerships with your suppliers. Transparency across the supply chain and collaboration will help to gradually improve the data quality over time. Another important tip for battery manufacturers is to aim at standardizing the data collection and reporting protocols across the supply chain. Consistency is everything. Second, automate the carbon emission calculation and implement quality checks. Also, given the complexity of the supply chain and the carbon calculations, digital tools are a game changer. They help fill data gaps and ensure more accurate calculations. Using digital tools will also help you to implement automatic quality checks to review inputs before finalizing calculations. This helps catch error early. It's a complex process, but with the right tools and partnerships, you can overcome these hurdles. We've been talking a lot about the challenges when calculating the carbon footprint, but it is important to keep in mind that the calculation and the strategic insights that come with it are crucial for the success of any battery on the European market. Nevertheless, the topic of calculating the carbon emission is still at its early stages, so you have to keep some of the previous learnings in mind when analyzing the carbon emission results of batteries where you did not participate in the calculation. First of all, uncertainties in data. Sometimes we have to rely on secondary sources, and their quality can vary, especially when it comes to emissions from raw materials or assumptions about energy mixes. Second, system boundaries. Are we looking at cradle-to-gate, cradle-to-grave, or cradle-to-cradle? Each scope tells a different story. Besides the scope, also exclusions like transportation or recycling can significantly affect the results, so it's important to know what's included. Lastly, the dynamic nature of supply chains. Carbon footprints are a snapshot in time. Supply chains are dynamic, and the numbers may not capture ongoing improvements or disruptions. So, while these results are a powerful tool for decision-making, they should always be interpreted in context. They're a starting point, not the final word.